I am the irrational number system. Let's start with a diagram. Real numbers, R for real numbers, composed of rational numbers on the left, all these sets of rational numbers over here, and then irrational numbers over here. So this is me. I'm over here in the blue. Some people think I'm a villain and cause pain in the math world, but I really think they just don't understand me. Most people think the rational numbers, these guys over here, are the real superheroes. Why would rational numbers be superheroes in the first place? Why? Okay, back to the diagram here. These are the rational numbers, naturals, wholes, integers, rational numbers over here. Why are they superheroes? Well, they have superpowers. So for example, the natural number system will always be your oldest system because it's the first one you ever learned. And when you started counting, you counted 1, 2, 3, 4, and so on, natural numbers. Integers have superpowers because they can be used in special things like golf scores, depth below the surface of a lake, and describing temperatures. You'll never hear it stated that the temperature is negative square root 5 degrees. Not going to happen. Now, don't forget the superpower of the fractions. So they're needed in a bunch of things, including construction, measurements, and recipes. You'll never hear it stated, I need pi over 2 teaspoons of sugar. So although the math world thinks that rational numbers are the superheroes, and I am the villain, I think it's because people just don't understand me. So let me help you with this. I'm going to introduce you to my 3 most popular minions in high school mathematics. Starting with my main man, pi. Did you know that if you measured the distance around the circle, which is the circumference, and then measured the diameter, which is the distance from one side of the circle to the other, passing through the center. Remember, the radius is half the diameter right here. But if you divided circumference divided by diameter, it would always equal this number pi, which is about 3.14, always. No matter how big or how small the circle is, always. Wow. My main man pi says, I can run circles around any of you rational numbers. I kind of like to think of him as my king. He's my number 1 in command. Very popular, used a lot in high school mathematics. He belongs to my irrational system, kind of like my king. Now, then there's my second in command, my minion that goes on forever without a specific part that repeats. So if there's a specific part that repeats, it's called a period. And that can be considered to be, it is a rational number. It can be converted to a rational number, a over b, where a and b are integers, b not equal to 0. But if it goes on forever without a specific period part, oh, that's irrational. Now, no rational number can do that. That's pretty special. Now, don't forget my exact numbers that can transform themselves. So all imperfect square roots, such as square root of 2, square root of 31, square root of 45, there's a whole bunch of them, too many to name, but they're all part of my group of villains, all imperfect square roots. These are all exact numbers, but they can disguise themselves when we approximate them as decimal equivalents. So this is their special power. So for example, the square root of 2, when you put in your calculator, it will yield 1.41421356 goes on forever, no period. Irrational number. We can approximate it to 1 decimal place as 1.4. I use the word transform, so they disguise transformation, so it's like a caterpillar transforming into a nice, beautiful butterfly. Okay, we need to talk about benchmarks here. So what is it? To assist in approximating an imperfect square root, one of my villains, remember all imperfect square roots are irrational numbers, one of my villains, we're going to use something called benchmarks. So in this context, a benchmark is a perfect square because it gives us an integer equivalent in close proximity to our value. So for example, suppose you're given the square root of 105. Well, we can use the fact that the perfect square root below that would be 100, square root of 100, and the perfect square above it would be square root of 121. We use these as benchmarks. Square root of 100 is 10, square root of 121 is 11. So that tells us the square root of 105 has got to be a number between 10 and 11. Now we can go a little bit further just by looking at the radicands and comparing. So if we have 100 and 121 on the ends, and this 105 in between, 105 is closer to which one? 100. So it should be a little closer to 10. So we could probably say 10.3, somewhere in there. Order. Now, since my minions have to take orders from me, I need to order them on a number line so I can find them quickly when I need them. So I got this number line, and I've shown perfect square roots. Square root of 1 is 1. Square root of 4 is 2. Square root of 9 is 3. Square root of 16 is 4, and so on. So what if then if I have something like, where can I find the square root of 61? Where are you, square root of 61? Ooh, right there. Got to be somewhere between the square root of 49 and the square root of 64. Somewhere in between there. Which one's it closer to? Take a look. Can we get somewhat of an estimation there? So it's somewhere between 7 and 8, but quite a bit closer to 8. I want to just introduce this idea of mutually exclusive to help us understand where I sit in this whole grand scheme of numbers. So just like you can't be a superhero and a villain at the same time, you're one or the other. You can't be a rational number and an irrational number at the same time. You're one or the other, but not both. What we say is they're mutually exclusive, so you can't be both at the same time. Ordering numbers on a number line. So this number line goes from -2 over here, that's -2, all the way up to +10. We've got 10 circled numbers on this line. They're going to match up here in a second in the chart. Right, so we've got these numbers right here. So we would like to first say, is it a rational or irrational number? And then where does it position on the number line based on these circled numbers 1 to 10? So let's do the first one. 1.25 would be considered a rational number. It's a terminating decimal. All terminating decimals would be rational numbers. And where's the position on the number line? So we come up here, 1.25. It's got to be between 1 and 2, and there's only one number between 1 and 2. That would be 4. So you'd put 4 right there. So now, if you wish, you can pause the video, try to complete the balance of these numbers. There's another chart like this on the practice questions, if you want to wait to then, or if you want to try them now. Pause the video, and we'll look at the answers right away. All right, so square root of 38, imperfect square root, irrational. Up here, number 7. Okay, we got two numbers between 6 and 7. Square root of 38, the perfect square below it would be square root of 36. So it's just greater, slightly greater than that. That's why it's 7. So it's closer to 6 right here. -1/2 is rational, would be number 2. Only one number between 0 and -1, -1/2. It's 2. Pi is irrational, 3.14, between 3 and 4, number 6. Square root of 42, it's an imperfect square root. One of my villains, it's irrational. Number 8. Square root of 100, it's a perfect square, which is a rational number because it's equal to 10. And it happens to be on the number 10. 0.2, terminating decimal, rational. It's number 3 up here, just past 0. And the last 3 are irrational. 159 is the position on the number line. 159 on the number line. Okay, so let's summarize. Rational numbers can be written in a particular form, a over b, where a and b are integers, and b cannot be equal to 0, can't divide by 0. That would be a formal definition of a rational number, which are the natural numbers, whole numbers, integers, fractions, negative, positive, but that's formal definition. Irrational numbers, my system, those that belong to me, they can't be written in this form. Can't be. Now, the 3 most popular irrational numbers typically in high school that you will find are the main man, pi, all imperfect square roots, and repeating non-periodic decimals. Remember that rational numbers and irrational numbers are mutually exclusive. They cannot happen at the same time. You're one or the other, not both. But when you combine the rational with the irrational numbers, it makes up what we call the real numbers that we deal with a fair bit. So when you hear this real numbers, what does it mean? Getting that grasp of it, it's the combination of rational and irrational. And then benchmarks can be used to approximate imperfect square roots and help to order them on a number line. I'm not really a villain. I'm kind of a nice guy, but hopefully you have a better sense of the irrational number system.